Okay, hi everyone. So we're going to go through the property of limits. What do I do when I'm adding, subtracting, multiplying, dividing? And usually I start off first with this, but because we are like a learn at home state, I figured it'd be easier for you guys to practice actively like doing limits than looking at the identities first, because the identities can be a little bit daunting, especially if you look here on the right side where it says property of limits. There's like a lot of letters going on. So I thought us first approach of practically using it and then coming back now and talking about these identity rules was going to be a little better. So if you look here, we have like properties of limits. So I'll be posting this cheat sheet. It's from a engineering resource website. And I also have one for calculus, so I can post that also. It's pretty good. And we're going to just go over these rules. Like what happens when I have a constant? What happens when I'm adding limits? What happens when I'm multiplying limits? What happens when I'm dividing limits? What happens when there's exponents in limits? So does this change from what we normally expect of these numbers? And how do we evaluate them? Okay. So your IXL work today will be um, calculating limits 1 through 5. It seems like a lot, but it really is just practicing our adding, subtracting, multiplying, and even plugging in numbers. Okay, so it's not going to take you that much time, but sure, it might be a lot of problems, but it's not hard. Okay, so let's go ahead and start a new one here. I want to talk about a couple of these ideas about limits. So the first one, go ahead and let's go back. I'm going to go over the rule. I'm going to talk about these rules here. Okay, so the idea is we're going to use two functions. One's called f and one's called g. One's called f. Oops. One's called f, and the other one is called g. And these are just functions. And you could say, to make our brains a little easier, maybe f is just the function 2 plus x, and g is just some function x squared. Okay, so just two functions that we know for the most part exist everywhere, especially numbers that we're going to plug in. And what if I ask you this question? What if I say the limit, let's do the first one, of a constant limit as x approaches a of a constant of f of x? Well, the identity is saying that, hey, since a constant is just a regular number, just like 3, it's the same thing as me writing the limit with a c posted on the outside. Okay. Now, why is this kind of helpful? Let's go to use our f of x here example to see what we're talking about here. If I say the limit as x approaches 2 of 75 f of x. Okay, seems kind of stupid, but see how 75 is a constant? That's a constant. Whoops, that was terrible. 75 is a constant for us. So instead of worrying about the 75, we can just write the 75 on the outside. And then we just write the limit as x approaches 2 of f of x. We know what f of x is. We know what f of x is. It's just 2 plus x. So this is 75 times, the limit as x approaches 2 of 2 plus x. We go ahead and plug in the 2, 75, and then 2 plus 2, which is equal to 75 times 4. Seems like a lot of work. But all this is saying is that whether the answer is, whether the constant is done before or after, it gives you the same answer. So here's something kind of cool now. If I told you the limit as x approaches 2 of x plus 2 is equal to 2, okay, you know this answer? You just plug that in. Whoops, not 2, it's 4. I don't know why I wrote that. 4. Every time I see the limit as x approaches 2 of x plus 2, that's just the answer 4. So this here is just the answer 4, which is really this guy here. Now, what if I give you a problem that looks like this? The limit as x approaches 2 of 3 of f of x. Well, that's 3 comes out, and just the limit as x approaches 2 of f of x. Hey, don't we know what this answer is? That's this answer here. So just 3 times 4. The idea of that 3 constant, it's just multiplying. And I can always do the multiplication of 3 afterwards since it's a constant. Okay. So to see that reflected, let's see if it's, actually no, I'm not sure that rule is on the actual website. But let's go and move on to the other one, which I know is. So what if I'm adding functions? The limit of, as x approaches, a of f of x plus g of x. And we draw a bracket to remind you, hey, this is one group. Well, this is the same thing as me writing the limit as x approaches a of f of x plus the limit as x approaches a of g of x. Okay. The idea is this whole function is the same as me doing each of these limits independently, separately. Whether I do them together or do them separately, they would give you the same answer. Now, using my kind of dumb illustration up there, x approaches a, f of x we said was 2 minus x, 2 plus x, I think. 2 plus x. We'll check. 2 plus x. And we said g of x is just x squared. Okay. So this is my idea. Well, I could also write this as the limit as x approaches a of 2 plus x plus the limit as x approaches of x squared, a of x squared. We can separate them. Well, why is that a big deal? Well, let's give ourselves a number. And I say the limit as x approaches, let's use number 3, of 2x, oh, darn it, 2 plus x squared. Would that be any different than if I did the limits of them separately? Would that mean any difference if I plug them in before or plugged it in after? Well, let's do the math. This would be 2 plus 3 squared. And this here on the right, this would be 2 plus 3 plus 3 squared. No difference. The rule is just saying that, hey, I get it. You have a new thing called limits. What happens when you add limits? Does it behave any differently before or after when we learn addition? And the idea here is that limits make no difference from what we had learned before. If we add them before, we're going to add them after. Why is this a big deal? It is because remember when we learned square roots? This is not always the case that things are just going to work out the way it's going to work out. If I ask you a square root of 2 plus 3, is that the same as a square root of 2 plus square root of 3? Oh, look, adding on the inside the same as adding on the outside. Is, looking at logs, the log of 2 times 3 the same as log of 2 times log of 3? Are these true? Is this true? Is it true? Like dumb things like 103 divided by 3 is 10. Look, they divide it out. What happens is whenever you learn a new type of operation in math, we have to make sure that our addition, subtraction, multiplication, exponents, they all work the same way that we thought they would. And if they don't, we have to redefine it because this was wrong. This was written, this is supposed to be log of 2, whoops. Sorry, this doesn't work. You can't do that. If I give you another log of 2, wait, no, I'm sorry. This would have been log of 2 plus log of 3. If I'm adding on the outside, I'm multiplying on the inside. You guys remember that rule? Okay. This one doesn't work. 103 is not divisible by 3. So we actually are done. This is actually supposed to be 103 over 3. A very popular algebra mistake is when you write 1x plus 2 divided by x. Oh, look, Mr. Ko, x divides out. Very popular algebra 1 mistake. Okay. So whenever we're learning a new operation, a new type of number system, we have to ask, if I add them, would they reflect the way I thought adding should be? If I subtract them, would they reflect the way subtraction would be? Multiplication, division, all my basic operations. So the cool thing about limits, it pretty much reflects everything that we thought it should have been. If I am on my left, I want to edit it, but whatever. Okay. On my left, if you look here, if I'm adding functions, inside or outside limits, exactly the same thing. What I mean is I can plug in a before or plug in a after, you will get the same exact answer. Whether it's a constant, adding, subtracting, or multiplying, you'll get the same results. Let's use this next one, the limit. Let's do multiplication. The limit as x approaches, let's say 2, no, let's not use 2, let's use 12, that's a big number, of f of x times g of x. Okay, using the same f and g from before. F of x was 2 plus x, and g of x was x squared. Okay. So if I plug in 12 into x, or 12 into x here, we would end up with, plugging beforehand, this would be 2 plus 12 times 12 squared. But if I separate it, the limit as x approaches 12 of f of x times the limit as x approaches 12 of g of x, well, if I plug in 12 here or 12 here, it's going to give us the same answer. Because I'm just multiplying, I'm plugging 12 into my variable. It's terrible. Okay, so everything we thought we could do with with regular functions, we can do with limits. Now, the next one, quotient is always a big deal because this is when we learn that numbers all of a sudden stop existing, like we become undefined. So if you look at division, they always tell you where g of x, right, the limit as x approaches a of g of x cannot be 0 because we cannot divide by 0 and expect for that to have the same exact answer. Okay, so this guy here on the denominator cannot be 0, because then we would end up dividing by 0. Now we've had problems where this had happened before, and on our last IXL, if I wrote x squared plus 6x plus 8 over x squared plus 2, no, not x squared, x plus 2, we say the limit as x approaches -2. Okay? Would this truly be the same as if I took the limits of them separately? Would this be true? Well, according to our clause here, see this clause here, where g of x, the bottom fraction, cannot be 0. If I did plug in -2, don't we end up dividing by 0? That means we cannot use this rule, right? Because it does equal 0. So what happens is, what we did is we went ahead and we didn't go forward with it. We went ahead, instead of plugging in, we tried reducing first. Limit as x approaches -2. And instead of breaking apart, we said, no, what? Let's just factor it and see if we can simplify it first. Okay, now we can rewrite it as the limit as x approaches 2 of x plus 4, plugging in the 2. Sorry, negative 2. Negative 2 plus 4 is positive 2. Remember that I have to keep writing limit. Once I plug it in, I don't have to write limit anymore. We always have to write limit till we plug it in and we don't have to write it anymore. The last one is exponents. What if I ask you the limit as x approaches 2 of f of x, and what if I square it, or even cube it? Let's cube it, make it worse. Cube it. Ooh, what if I cube that function? Well, this is the same thing as us cubing our answer afterwards. The limit as x approaches 2 of f of x. We said that f of x was 2 plus x. Well, if I plug in 2, hey, let's plug in 2. We said 2 plus 2 is 4. So this could be rewritten instead as just 4 cubed. Do you really want to write 2 plus x, cube it? Do you want to cube it first before we plug it in? Right? Do we want to cube it first and then plug in the 2? I think it would be easier if we plug it in and then cube it afterwards. So this is what that rule allows me to do. So say, hey, you know what? You're cubing something, I get it. Worry about it later. Now, let me give you a really lame example. What if h of x was just x? The limit as x approaches 2 of h of x to the third power. Well, this problem would be easily done. This could just be limit as x approaches 2 of x cubed. And then we can plug it in and plug it in now. So it's going to be 2 cubed. Well, if we rewrite this, we could write the bracket on the outside. And what's the limit as x approaches 2 of h of x? So look here, if I plugged in 2, plug in 2 and plug in 2, isn't x 2? This is just 2, and we're going to cube it afterwards. So essentially, we are kind of taking the same amount of steps, but understanding that whether you square it or not, it's just like a regular problem. It's going to behave the way we thought it was going to behave. Now, what are we going to do is we're going to put all this together in a polynomial. The limit as x approaches 2 of x squared plus 3x plus 2. Okay? And we're going to use all our rules. We use all the rules that we just covered on the left. We have exponents in the problem. We have addition in the problem. We have constants in the problem. Okay? So I'm going to write it out the long way. And after I write it out the long way, we're going to not write it out the long way anymore. Again, the idea of these limit definitions are definitions of what the ground rules are. What can we do? Something kind of interesting, like in soccer and basketball, are very different how they treat out-of-bound lines. Out-of-bound lines. Example, if you play soccer, can the player walk off the court? In the sense that, can the player's feet be outside the boundary line? Answer is yes. But in basketball, you can't step outside the court. So these are our boundary. These are our game rules. So let's do it the long way. The long way is if I separate this into 1, 2, 3, because the plus sign, this is really the limit as x approaches 2 of x squared plus the limit as x approaches 2 of 3x plus the limit as x approaches 2 of 2. In our first section here, we have exponents. The limit as x approaches 2x, where the exponent goes on the outside. That looks a little terrible. The next one, hey, 3 is a constant multiple. 3 limit as x approaches 2 of x plus the limit as x approaches 2 is just 2. That's a constant. The rule here is a limit. Here's the rule here. Limit as x approaches a of a constant. It's just like a constant. It doesn't change. If I told you my height is 6 feet tall, my height is going to be 6 feet tall no matter what time of the day you call me. Okay. If I plug in 2, what's the limit as x approaches 2 of x? Plug in 2, x is now 2. This is 2 squared plus 3 times 2, because plug in x is 2, plus 2. This becomes 4 plus 6 plus 2, which is 12. Ms. Ko, you did all this work. What's the point? Couldn't we have just plugged in up here 2, 2, 2? Because if we did that, that'd be 2 squared plus 3 times 2 plus 2, which is 4 plus 6 plus 2, which is also 12. So why'd you go through all that work? Why couldn't you plug it in right in the beginning? It's because limit is different than function. Remember, if I wrote f of 2, don't we just plug in the 2? How's that different than me writing it this way? It's because this is, and this is what it should be. Remember, limits and functions are slightly different. Functions say, what should it, no, what is it? What would it be when I see 2? Limits say, what should it have been? And oftentimes, yes, they are the same exact answer. They're exactly the same, they're exactly what they're supposed to be. But if I gave you the problem, the limit as x approaches 3 of x squared minus 9 over x minus 3. Okay. Can I really plug in 3? Does f of 3 really exist? It's a 0, 0. That value doesn't exist, does it? But when I write limit, I say, what should it have been? I get it, it's 0, 0. But what should it have been? X plus 3, x minus 3 over x minus 3. And limit says, hey, I get it, it was 0, 0. It shouldn't have worked. But the limit, it should have looked like, 6. So for the most part, oftentimes we do have overlap. 99% of limits are exactly what you expect them to be. But look at this here. Nope. It was going to give us undefined, but it should have looked like 6. So when we're looking at these easy problems, don't take them for granted. Yes, really, we're just plugging it in. But when it comes to questions when we end up with an indefinite, or problems that look a little funnier, where often have the fractions, we have other techniques to still say, hey, I get it, it doesn't exist, but this is what it should look like. And actually, that's why we have all these rules here, not to deal with, whoops, I hate when this happens. Not to deal with what it should be, but what it is, oh gosh, not to deal with what it is, but what it should have been. And this is what all these limits problems do. Now, all these rules on my left-hand side pretty much allow me to do problems that you see on this example here. They allow me to do polynomials because of the exponents, because of the constants. They allow me to do fractions, just like one below with the rationals. So these rules are just allowing us to do what we expect us to be able to do, adding, subtracting, multiplying, and dividing. There are some rules here also on the left, just talk about as we go to infinity, just different rules here. Okay. Okay, let's look at some quick IXL problems, just as an example what you guys are going to do today, and then we'll call it a day. So you guys are doing Excel. You guys are doing F1, 2, 3, 4, 5. Okay. First one is adding, subtracting, and the multiplication laws. Okay. Now, here is the statement here, and these are my values. Okay. So let's rewrite this. On the right, the limit as x approaches -4 of h of x plus g of x. Hey, well, it's a plus sign. We can separate that into two separate limits. Okay. Now, the cool thing is that the prompt gave me what each of these variables meant. So this is just straight plugging in the answer. What is the limit as x approaches 4 of g of x? What does that look like? Hey, isn't that this guy here? This one and this one are exactly the same thing. So I'm just going to write, this is now just 7. How about g of x? Well, look here, isn't this guy and this guy exactly the same thing? Well, we're going to say now you are 2. The answer is 9. Again, we're using our rules, breaking them apart so that we can use the identities that are given. Something synonymous with this would be if I wrote g of -4 is equal to 2 and h of -4 is equal to 7. What is g of -4 plus h of -4? Okay. Except all the difference that they did is now instead of plugging the 4 first, they said call their limit. What could it have looked like? Okay. We said it was 9, right? Okay, what if I subtract? We follow the same rules for subtraction. Let's jump up to something a little harder. Multiplication, the limit as x approaches 1, we're going to split it, and the limit as x approaches 1 of f of x. Guess what? We have both of those already given. Because we don't have the overall one, we had to separate them first using our rules. And that's going to be -2 and 8. It's going to be -16. I'm just going to move on. Okay, that's the first one. Let's see. Using division law is just working on division problems. Okay. So is g of x 0? Is g of x 0 here? Is g of x 0? No. So we just rewrite it as k divided by g. K divided by g. -4 over 9 is -4 over 9. Okay, because k is on top, g is on bottom. Okay. Next one, we're not dividing by 0. Hey, just plug in f of x. This rule can be rewritten if you want as a constant multiple. The limit as x goes to -13, 1/2 f of x, constant, you can go to the front, limit as x approaches -13 of f of x. This is just 13. So it's just going to be 13 divided by 2. Okay. Jump to something a little more tragic. No, they're all the same. Go more. So looking here, is G or K0? Is there enough information to evaluate this? As long as the denominator isn't 0, we're perfectly fine. What's 0 divided by any number? This is 0. Okay, take a look. K of x is on top. K of x on top, and then G of x is on the bottom. K of x is 0. G of x is -3. 0 divided by 3 is 0. Is there enough information to evaluate this guy, where G of x is 0 on the bottom? So we're going to say no. K of x is on top. How about, is the denominator going to be 0? Can I plug in that 0? Nope. Okay, so something to practice. Okay, let's move on to XXL. Powers and roots. So the idea is the exponent can go on the outside. We know the inside's 2. 2 squared is 4. Okay. Gets a little harder probably. Let's jump up. Square roots. Same idea. The square root is a 1/2 exponent that goes on the outside. Let's rewrite this. Let's actually show the work. We're going to say this is equal to the square root of the limit as x approaches -5 of h of x. Hey, we know what that is. That is just the square root of 25. That gives us 5. Okay. Move on. Move on. Okay, that's it. Next one, find limits using limit laws. So this one would be a little more tough, but please be advised. Aren't we just adding and multiplying? Look at the problem here. I'm just adding and multiplying. And those are basic operations. There's nothing wrong with that. We know that the limit as x approaches 3 of f of x, we know that is 2, plus the limit as x approaches 3 of k of x. We know that's going to be -2. The limit as x approaches 3 of h of x. Well, that over here is 4. Now, what's the difference between just plugging in the 3 in? Nothing. You could do that. But the reason why we can do that is because if I write it out separately or plug it in, it gives us the same exact answer. So we defined our rules so that we can make our life easier. Don't write this anymore. Just know it's true. Instead, just plug in f of 3 plus k of 3, h of 3. So you just plug in the x like we do with regular limits. Okay. Let's see how much harder this gets. Same. Careful. X is 0, so x has become 0. X of 0 is 0. Okay, so pretty much doesn't get any much more difficult. Well, no. Okay. Last one. Polynomial functions. Same thing before. We're just gonna plug it in. Plug in -4. Okay. That's it.